Where we left off with 5 is we looked at the JIT and building a JIT file, like creating the kernel where all the includes come in and all the defines. And then the next step at the end of that session, I just watched that session. We talked about going over how they get compiled, how they get run, loaded, I guess looked up, like now that we've got the JIT, the JITted function created, how is it
Right.
compiled and loaded in?
Okay, so you still okay, yes. We haven't I haven't looked we haven't really looked at the internals of the JIT. How does it do all
Right.
of well, we've looked at some of the internals of the JIT, but not stuff like how do I load the kernel? How do I keep track of it? Because I need to come back to it.
Mm-hmm.
I
Maybe a
don't
little
want to
bit about like
have.
how you invoke I assume you use like os.system or something as system
Oh
call
yeah,
to
how
invoke.
do I
Yeah.
actually go and compile it? Yeah, I haven't
Yeah.
showed you that either. That's right. That's right. How do I compile it? How do I link it in? Um, this cat is pestering me here. How do I link it in? Yes, I've not explained that yet. I could do that. Okay, so yes, let me. Okay, so I've got GraphBLAS sitting up here on my desktop at work. And I'm just doing some test coverage. It's not 100%. I've got one statement uncovered.
Oh, it's always it's the
Yeah,
last little,
the last one. Yeah, it's like,
you
oh,
know, who covers the coverage.
yes, yes. Okay. So what is this? What is doing here? Huh? What is happening to my screen?
Is the Zoom messing with you? I
I don't
see.
know. This window's not.
Oh, I see it's like
I
missing a.
can move this window. I'm trying to like see. I can it highlight it. It's not even. Well, that's really weird.
Did you
So
X over? Is that the?
I can't even exit.
I
I
meant, did
can't
you use
even
X
move it.
Windows to run a remote shell locally?
Yeah, no, I'm not using X Windows. This is a local shell.
Oh, okay. Yeah. Because you said your desktop at work. I assumed you were remote
Here,
logged
close
in.
window. There we go. I'll just close it. There, it's done. Okay. Yeah, I am, but this window here is a local window, but I'm SSH'd.
Hmm. Have
Yeah.
you ever heard of Mosh? MOSH?
No,
It's persistent SSH sessions over UDP. So
Oh, okay.
you can mosh into your work server and then shut your laptop and go somewhere else and open your laptop and you're still in the session.
Oh, okay. I use Screen for
Yeah.
that.
Well, but Screen keeps your processes persistent on the server, but you still have to SSH in and reconnect your
Yeah,
screen. But
right.
Mosh, that's all. You'll never type SSH again.
Oh, okay.
Yeah, so something to look into, and it works over SSH. So you just install
Oh, I
Mosh,
see.
and then instead of SSHing, you use Mosh, and then you never like you can shut your laptop, open it, and
I see.
you're back. Yeah,
Okay.
it's a stateful
A
terminal.
stateful SSH. Yeah, I
Yeah,
see.
stateful SSH. Yeah, it's really
Got it.
super hand. It saved me like a whole year of my life just not typing SSH.
Okay, so let's look at is this font? I can make it bigger.
I could see it. I mean, maybe the
Is this
recording resolution, maybe for the resolution.
yeah, maybe make it a little bit bigger. Um,
The videos look pretty good, um, but there's a bit of grain,
yeah,
pixelation, grain. So old pixelation.
yes. Okay, this is probably good size. All right.
Yep.
So I've got this by the way, this again is GraphBLAS 9.3. It's not released yet, but I'm going to try to release it soon. I'm doing test coverage on it. I've got, one statement not covered yet. Okay, so the JITifier. This is a rather big file, jitifier.c, and also the jitifier.h. Okay, this is the workhorse current core of my JIT, these pair of files, where everything else, I mean, I've shown you this notion of encodify, enumify, macrofy. Those are all broken up into their various pieces. Okay, but the core of the JIT is right here and right here. And I also have some file commands, and those are like low-level things, like how do I lock a file, how do I open a file, that sort of thing, because it's for portability. Okay, but those are very low level, like how do you lock a file? It's Windows versus POSIX and such. So this is like these are just very low level file functions, but the core of the JIT is right here. So the JITifier and everything else is the encodify and such and macrofy are outside of this. The reason I defined it this way is because I need some static memory. Okay, I don't like globals. Globals are evil, right? But I have to have them here because you call GRBMXM and I JIT a kernel and I stick it in a hash table, and you call it again and I say, oh, I've seen this one before. I've got to go find it. The function pointer to the GRBMXM kernel, not GRBM itself, but the JIT kernel internally that I have to call. So I have to create a hash table that then is persistent across my GraphBLAS session. And a lot of other persistent information, not just the hash table. I have some strings, like a string that has defines the path to your cache folder, where all of your source code is, where all of your compiled JIT kernels are. I need to know where those are. I have another string that says, what's your C compiler's name? What's its path? What are your C flags? All these things I have to maintain in this global state. So what I did to make this work then is every time you're inside this one GraphBLAS session, every call to GraphBLAS is going to access these globals. Now, if you start GraphBLAS, and then in one of your own processes, user process, and then you have a thread, you say create two threads. They each call GraphBLAS. They will talk to the same hash table. So I have to place all this work inside a critical section. So there's a lot of critical, there's a lot of named critical section in here, OMP criticals here, to protect against that. And so that because I want them to share it, because if one user thread compiles a JIT kernel, goes into JIT cache, the other thread wants to use it. They have to share it. So the hash table is protected with a critical section. Normally, a user application is not going to do this. Normally, all the parallelism will be inside GraphBLAS, in which case, every time I talk to the hash table, there's no competition, there's no conflicts. There's no conflicts for these critical sections. But that critical section is really important. Now, there's another layer. What if there's a separate process? Two GraphBLAS processes could conceptually share the same JIT cache. It's a file folder. So that's why I have to use file locking as well to protect that, so that they don't step on each other. So there's multiple layers of synchronization I have to worry about.
And the hash changes if the two processes are wanting slightly different kernels, right?
Yes, the hash depends on whatever the enumification says. Like MXM with A is sparse and B is hypersparse, and there's a mask that's this, and here's your semiring, and so on and so forth. And It has zombies. It doesn't have zombies. It's a different JIT kernel, potentially, with zombies or
Yeah,
not.
cool.
Is the matrix ISO valued or not? It's a different JIT kernel in that case. But if everything lines up, if that's all the same, then it's going to be the same. It's going to map to the same enumification. It's going to have the same hash function. It's going to be the exact same kernel in the hash table, the same function pointer, identically all the way down. And that can be shared by two GraphBLAS user threads within a user's process, single user process, one called a GRB init. Then you can have the user can have a parallel pragma OMP, and that each call GraphBLAS. You can do that. You just have to follow the rules. You can't have two of those user threads write to the same output matrix, but they can both read the same input matrix. That's part of the GraphBLAS spec. If they want to share stuff, like one thread creates something and the other thread reads, you have to use a GRB wait to do that handoff. Okay, and there's two kinds of waits. I support all of that. That all works, and yet they share the same hash table, so you don't JIT the same thing twice. Okay,
And
so
some of these questions I'm asking are for other people watching the video.
right, right.
And also to clarify, two different processes have to be using the same version of SuiteSparse for the cache folders to line up, right?
Yes, they do.
Yeah.
If two processes use different versions of GraphBLAS, then by default their cache folder will be different.
Okay.
And so by default the cache folder is, like on Linux, it's .suitesparse/grb930. So if you have a different, like 931 or 921, it's a different folder. If you somehow mix, like you can tell me a different cache folder, and it doesn't have to be grb930. It could be, here, GraphBLAS, go use this. If you tell that to two different GraphBLAS versions, you're going to have a lot of conflicts, because what's going to happen is you'll have one cache folder with GraphBLAS libraries that are compiled for two different GraphBLAS versions. That's a horribly dangerous thing to happen. But I protect against that. What I do is when I load in a kernel, I query it. Which GraphBLAS version are you compiled for? Because I'm 930. What? This is a 921 kernel. Throw it away, recompile it.
Because you wrote a little struct into the file or something that statically states. Yeah.
So what I do, if you look at .suitesparse, you look at your, say, grb930 folder. Okay, gonna have 19,000 kernels, because I just ran my test coverage. I compiled 19,000 kernels. Obviously, I'm not gonna try to look at all of them, but here's some of them. Say, I don't know. Here's a transpose with a unary operator, whatever it is. It's transposing and taking the absolute value. So it's absolute value of a transpose for uint8 data types. Okay. And so it's doing a transpose, and it doesn't look like there's typecasting going on. All the matrices are, oh no, and there's a typecast. The input matrix is double. So it's a transpose and a typecast and an absolute value. Okay, you got all that?
Yep.
From double into uint8. Okay, so that's the kernel. All right. And so there's my transpose kernel. And transpose and apply unary operator at the same time. All right. But every kernel every kernel JIT kernel I compile is in Linux, it's a .so file. So this is going to compile into a .so, and it has two entry points, two functions here. The kernel itself, which is going to be inside this, and it's going to have this name. By default, if it's a runtime kernel, it's called gbjit kernel. If you're not in runtime, if it's a pre-JIT, you're going to have a full-fledged out name. Okay, but I also have the query. So when I load a library in, I can query it. It's like, who are you? Like the hash should better line up. And there's the version 930. I can call this function to return to me the version it was compiled for, the version of GraphBLAS it was compiled for. And if I'm GraphBLAS 920, if this doesn't match exactly down to the last version number, I throw it away and recompile. And this is all null. These are strings. And I don't have any here because there's no user-defined types or operators. But if
Right.
there were, the strings would be there as well. So if you change the Gaussian add function, say, which adds two Gaussian integers for the Gaussian data type, if you change one character of that function, that user-defined operator, even if it's a comment, I don't know, it's different. I'll
Sure.
say the string's different. I got to recompile the thing. And I do that on load time. So I handle all that. But if it's this, if the operator is the same, if the strings match, if the version's the same, we're good to go. So that's the query idea for that. I have protection against that. So that's what I do. And to manage that. So you can tell me to say, hey, Tim, hey, GraphBLAS, don't use that folder. Use something else. I was like, okay, cool. But if there's old junk in there from an older version of GraphBLAS, I may hit it. I may think, oh, there's the one I need. I load it in. I say, what? This is the wrong version of GraphBLAS. I delete it, the file, and I recompile it as if it wasn't there. So, but to protect against that by default, I put it in a different folder name as a default. And in Windows, the same thing. It's like local app data SuiteSparse GRB 930.
Cool. Yeah, we covered most of this in the last session too.
Okay.
Yeah. So it's a
So
good synopsis.
yes.
Yeah.
All right. So let's look at say the workflow for say I think reduce is the simplest one. So let's look at for reduce to scalar. So reduce to scalar comes along and says, hey, I'd like to use the JIT. Oh, okay, cool. So this is the GraphBLAS function that's doing reduce to scalar. And it may use a factor kernel, it may use it to the generic kernel, but at this point it says, let's try the JIT. Okay, so this calls a JIT wrapper GB reduced to scalar JIT.
And sorry, just to step in, that no value test is like, let's try this next sort of thing. Like,
yeah,
right?
No value I use internally to say, I've called a function and it says, sorry, I don't feel like doing it for you. Oh,
Let's try the
okay.
next step. Yeah.
We'll go down the layer. And so this will be, so info starts out as no value. I don't return this to the caller, but no value is used in a very specific way in the GraphBLAS API. Like you've asked for an entry in a matrix and it's not there, you return GRB no value. But I just repurposed that info to use internally because, for example, maybe the CUDA, maybe GPU can do it. Maybe GPU says, nah, I really don't want to do it because the data type is too big. So on CUDA, we can't have data types bigger than, I want to say, what is the size we can handle? There's some maximum data type size we can handle at the moment. I want to say it's 32 bytes, but it might be bigger than that. No, I think it is bigger, but it might decide it's too big. So, okay, fine. The GPU says, nah, I refuse to do it. In which case info will be no value. Okay. And if you come here then, oh, info is no, or maybe you don't have CUDA, so it's compiled out. So, hey, I haven't computed yet. Well, let's try the ISO case. This is a built-in, this is a built-in kernel for any reduction. But let's try the factor kernel when there's no typecasting. Because maybe it's a built-in. Oh, the switch case says, oh, I don't have that operator, or it's been disabled, or whatever. Okay, well, let's try jitting it. Well, maybe the JIT's turned off, or maybe you give me a function or user-defined operator, but you haven't given me the string. So I can have a function pointer. I can't JIT the thing. The JIT's going to say, tough. Okay, then I have to go punt to generic. And if you
Mhm.
look at the Burble, anytime you see the generic, you know it's going to be slow. That's going to go through everything as a function pointer. Every operator, one plus will be a call to a function. Every scalar assignment's a mem copy. Every typecast is a call to a typecast function pointer. Everything, so there's one algorithm, and that's this right here. Or well, I have four algorithms, I guess, four cases. Um, and so, but we're here now with the JIT. So we decided to use the CPU, the OpenMP JIT. We might use the CUDA JIT, which is up above, but we decided to use the. So everything that ends with underscore JIT is a JIT wrapper, and that's the GB reduced to scalar JIT I call here. And then then this talks to the JITifier load. So now we're in this function. Okay, so I've talked about at length at the encodifying process. That is not going to this JITifiers.c file because this doesn't need the access to this global information. It doesn't need access to the hash table. It does compute the hash function, but it doesn't compute doesn't look up the hash table. It doesn't ask where the GraphBLAS cache folder is. It doesn't need access to any of that. So it's outside of this file. But now we need to actually give me the function pointer right there. That's the result of this is give me the function pointer so I can call it to do the work. Okay, so this has to take this and codifying, look it up in the hash table. If it's there, return the function pointer. If it's not there, write the thing, or maybe load the thing. And if not loaded, compile the thing, stick it in the hash table, return the function pointer. So this is the main entry point from the rest. The primary entry point from the rest of GraphBLAS is right here. JITifier load is the primary entry point from the rest of GraphBLAS into the JITifier. Is this function? Most of the other functions in here are things like I don't know this. I'm trying to think if some of these sets and gets for strings will be called outside. But let's just focus on the load. Okay, this is a big file. This is 2,700 lines of code, and I maybe should split it into separate files. But again, then I'd have to have global variables, and I don't want that. I have just statically defined variables that nobody can see except for this file. Okay, so I come in. So the path for this is the following. I can disable the hack. I have a hack to disable it for testing. That's not only used in MATLAB. Okay. The JITifier now it has several layers. The first is the hash comes back and says there is no hash. This will happen if it's a user-defined operator that doesn't have a definition for the string. And the hash is infinite. It's UN64. I reserve that hash function result for that one case. It's an unjittable case. So I say, sorry, no value. You don't have it.
Go generic.
Go generic. And there, I don't have it, so that gets, and I don't call it here. Yeah, then we go generic. No value again means I refuse to do it. I can't do it, or I refuse to, or whatever. Because I may, in a sense, be able to do it, but I've been told not to. Because there's 5 levels of the JIT. There's off, which means no, even if it's in the hash table, like the hash table is empty, even if it's a pre-JIT kernel, turn it off entirely. No JITs, no JIT kernels, not even pre-JIT kernels. So always return no value. If it's the second one up from that is pause. That means don't load anything from disk. But if you have a kernel that's already in the hash table, well, you can use that. That's pause. So off, pause. The second one, oh, sorry, no. Pause means, sorry. Off means the hash table is empty as well. That's flushed out the hash table. Pause means turn off the JIT, don't use any JIT kernels, but keep them in the hash table. That's pause. Run says, if it's in the hash table, you can call it and use it, but you can't load it from disk. You can't compile anything. But if you've already compiled and loaded it, you can use it if it's already in the hash table. That's run. And that's going to be a very common case for, say, FalkerDB, or maybe NetworkX, where you want to exercise GraphBLAS, create it in development. So say you're the NetworkX developer. You exercise GraphBLAS. You turn on the JIT entirely, not to run, but to full on. You let GraphBLAS compile all its JIT kernels it wants to, and you run through all its paces. You get 100, you get 1,000 JIT kernels. You're done. Now you want to distribute this to the world. So you take these JIT kernels, you put them back into GraphBLAS as a pre-JIT kernel, you recompile GraphBLAS, and now they're baked into GraphBLAS as pre-JIT kernels. And then your end user, you only let them set the JIT to run, which basically says, use the JITs that are there, don't try to compile anymore. You don't need a compiler. And that's really useful for things like here, you want to run it on iPad or iPhone. Hey, there's no compiler here, but you maybe want to use GraphBLAS here. You want it to go fast on those kernels that you need. So outside of the iPad, you can run GraphBLAS through it inside its application, let it compile a bunch of kernels, lock it down, finish, take those JIT kernels you want, stick them back into GraphBLAS, recompile, and then give that recompiled GraphBLAS with the extra kernels, the pre-JIT kernels, to the iPad, no compiler. Turn it off.
Sort of a cross-compiling sort of pattern.
Yeah,
compiling
yeah.
on one,
you compile
copy
it
over.
one, and then when you copy it over, you cross-compile to the iPad, but you cross-compile it with the JIT turned off, or turned to run. I'm sorry,
to run,
not off,
yeah,
just to run. And the reason, and there's another feature I recently added here. Let's see. The system command is protected with the JITs turned off. So this is a little bit brute force. So I have to fix this. But anyway, so because the iPad doesn't even have a system command. It's turned off.
There's no
You
shell.
can't even call.
Yeah.
You can't call system from an ANSI C or code that you run here. It won't compile for the iPad, probably for the iPhone. iOS doesn't. You can't compile code on the iPhone that calls system. It doesn't even let you compile it. It doesn't just say, sorry, I can't do it at runtime. It just doesn't even compile.
Yeah.
Or link. So that's the off or pause case says, well, there are no. You're not going to use a JIT kernel, even if it's in the hash table. Okay. Now, if there's a special case for the JIT run case, here the hash table, in the run case, the hash table is read only. Okay. So that means that in the run case, and there's two JITs I don't do this for, two types of JIT kernels I don't do this for. But when you're just running, I don't need to enter a critical section. I can just look it up in the hash table and return the function pointer if I find it. So I have the JIT lookup. This accesses my hash table of JIT kernels. And it's a hash table of a structure that I have defined. Where is it? I'm in the source reduce. I want to go to the JITifier. I have a, where is it? It's going to be defined here somewhere. Yeah, this is my hash table entry struct. It's on the order of, oh, let's see. This is 16 bytes, the encoding. It's got the 8-bit code, which could expand in the future because the MXM is using 63 of those 64 bytes. It's got which kernel it is, and it's the length of the string if it's a if it's not a built-in. And then the entry, the hash entry, has this encoding, but also has the hash function. It has the actual string itself, the suffix, which includes the operators. And then it has, so this is a malloc pointer. And then it has the DL open for the library for DL open close. And then it has the actual function pointer to the kernel. And then it has a pre-JIT index, which I have, let's see, this is for pre-JIT kernels. So this is a very small object that goes in a table, which I look up in the hash table here. It's like, do I have it? Okay, oh, I got it. I found it. And if I find it and it's already been loaded and checked, I can return the function. There you go, you're good to go. So that has to happen really fast. This is the greased, well, this is a greased lightning path for the run case. I don't even have to enter a critical section because I know nobody that is within this GraphBLAS nobody within this GraphBLAS context, GRB init to GRB finalize. If the user forks off several threads, this JIT status is shared by everybody. This is everyone shares the same JIT status run. So nobody's going to be touching the hash table. So there's no critical section here. Look it up and go. Otherwise, oh, I didn't find it. Okay. So now I've got to go into critical section because now I've got to maybe load it from disk, or maybe I have to compile it. Or maybe the JIT is turned on and so I have to access the hash table in a critical section because someone else might be compiling a different kernel and accessing the hash table. So I do it in a critical section. There's a potential performance bottleneck here. I only compile one kernel at a time inside the critical section, always. It's just too dangerous. I tried to figure out how to, because what if there could be different kernels, right? What if they're both threads want to compile the very same kernel? Ooh, right? Your brain explodes. How do you? So those 5 states of the JIT: off, pause, run, which means the hash table's it's not going to change. The next one is load. This means I can load I can either use a pre-JIT kernel, it's already in the hash table, or if something's not in the hash table, I may load it from disk, but I can't compile. From on means everything. I can
Everything.
compile, load, everything. So if it's off or pause, you don't get the JIT. If it's run, you can get the function if it's already in the table. Otherwise, I have to call the secondary worker inside a critical section. The rest of the work is done inside a critical section. And this is the rest of the work right here.
Can we take a couple minute break real quick?
Yeah, sure.
I'm going to pause the recording here. All right.
Okay. So now I've got to do the work in the critical section. And so the goal of this method here is to produce the function pointer. And it may need to compile a kernel or maybe to load it. It may already be in the hash table. So I just have to look it up. And if I find it, great. So what is the input to this? This is everything that came, most of this stuff, like I think all this stuff. Yeah, it's the same parameters. This is what was given to me by the JIT wrapper. What's the JIT family? What's the name of the kernel? What's the hash code? The encoding, that's the suffix, the string. What are the GraphBLAS semmering monoid operators and types you're working with? And so I'll use some or all of these depending on the kernel I'm compiling. Not everyone would use all of those parameters. So I can continuing now though the same parameters, but now inside a critical section. Okay, so now the process is I first look it up in the hash table to see if I can find it. Um, 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 it comes out, this is the output of this lookup. It's in position KK. And K1 is an index into a different table. Okay, that's this puppy right here. So this is the position of the hash entry in my hash table, KK. So I got it. I found it. Oh, yay, I found it. So I also return the pointer to the function, which is just this one here. But I also know where it is in the hash table. This function has three outputs, basically. The function pointer, which is this, and then the index of like which entry is this in the hash table. So there it is. I get the entry. Great. Okay. However, I may have found a prejit kernel. Now, a prejit kernel has been baked into GraphBLAS already. I don't have to compile or load it. It's just sitting right there. But it's in a separate list. Where's the list? Which I've attained by calling. I can attain that list by calling this function, which is configured by CMake. So I get this table of all the prejit kernels. I look up at position K1 and I get a query. I have to ask, well, is it valid? Like maybe I compiled it. Well, I don't even know if it's valid. Why can't I know that at compile time? I can't. Because you may have had a prejit kernel baked into GraphBLAS, but now at runtime, you've given me a different definition, different string of, say, the Gaussian add has a different definition. So I have to check it. I have to check the query function. So that's the jitify query call. The jitify query is going to check the kernel to say, check the compiled kernel to make sure it's okay. It matches what I expect it to have. The right GraphBLAS version, the right hash function, the right strings, definitions, and everything. The monoid has to have the same terminal value, or the monoid the identity value, or whatever. Everything has to match. And if it's okay, I've checked the prejit and I return success. I've got the function pointer. This is my final output. Okay. If I don't like it, I say, wait a minute, this is a stale prejit kernel. I remove from the hash table, so I'll never see it again. It won't be in the table anymore, and I won't put it back in there. So it's in this list that's been configured, but I'll never use it again. I free it. And I don't return, so I'll drop through to go compile one if I can. So that's the prejit handled. I have a few special cases for how user operators and user types are handled. Because their check is slightly different. And I check them every time, I guess.
Because they can be made at runtime.
Yeah, and I only call this thing when I don't care about performance at this point. So what is a user op? I'll show you an example. If you give me a user-defined operator and you just give me the string, you don't give me the C function pointer, I can still work with that. I'll compile it myself. And I only need to use the function pointer in cases where I don't care about performance anyway. things like reduce an ISO valued matrix, a billion matrix of all value, a matrix of the billion entries, and all the values are 2. And you've asked me to do a reduction, which is the plus reduction. The answer is 2 billion. And I don't need to call a high performance kernel to answer that. I can call the operator 30 times the log 2 of a billion, and I'm done. I can do plus it with a log n time. It's like compute x to the n with log 2n multiplies, right? Repeated squaring. You do the same thing for any operator, and you can get plus. You use plus multiple times to get. But so I don't care. Well, 30 times. I don't care how slow the function pointer is. I don't care. I'll check it every time, and and the one of those examples. I'll show you some examples of that. Here we go. I have, I guess, yeah, my gunk. I think I've just messed about with this in my tests. So here is a function. This is a JIT kernel, but all the sole goal of this kernel is to return a function, a pointer to this function right there. That's its sole job. And I can still query it, but this template here, it does one thing. It returns this function, a pointer to that function. It doesn't call the function, just returns the function pointer. And it's a function pointer which just does a copy of a bool to bool, right? So why am I doing it? Well, this is one of my tests, right? Why
You're
not?
testing it, yeah.
Yeah, and then I have my own int32 type. It's like, why not? The type def is just int32. So why did they use int32? Well, because this is just for testing. And this is a kernel where, see, in SuiteSparse GraphBLAS, you can say, Tim, here's a type, GRB type new, and you give me the string. And in this case, the string is type def int32 my type, right? There's the string you give me. And well, you also have to give me the size of that type. But what if you're Python or Julia and you just say, well, here's my type. I can create a string from Python or Julia with the type that the struct in it. I can create a string from Python with the C struct in it and say, please use this as the type. Well, GraphBLAS says, yeah, but tell me the size. And Python says, what? I don't know the size. Ask the C compiler, right? Because what if you have a struct with padding in the middle? Oh my goodness, right? How do you know the size of the thing? That's what this job does. What you do then in GraphBLAS, SuiteSparse GraphBLAS, this is an extension. You give me the GXB type new, you give me the string that defines it, and instead of giving me a size, you tell me the size is 0. And I'll say, yeah, right. It's not 0. This means you don't know the size of the type. No problem, dearie. I'll compute it for you. And that's what this does. Like to compile, I have to go talk to the compiler and ask it, how big are you? That's the sole purpose of this job, is to return size of this type, which is 4. Call it once. Okay. And that's what this one it does. What does it do? I check the string here and return success because now the function pointer can be then called, but I also query every time you look it up. So this, I want to do the query every time here. I don't always do the query. Okay. So if I look it up, I only query it to make sure it's okay in several cases. First, if it's in the table already, if it's a standard JIT kernel, I just trust it. If it's a pre-JIT kernel, I check it just once, the first time it's called. And then I set a flag saying, you've been checked, you're good. And if you're bad, you get deleted from the hash table. So the second time around, for a pre-JIT kernel, this code wouldn't be called. If it's a user operator, I always check it every time because I don't care about performance of this because this is not inside a high performance kernel at any point. Same thing with this. I always check it. Okay. Otherwise, I have it. Good to go. Okay. Now, what if I fall through? Like, for example, the type changed, the operator has changed, or you've turned off the pre-JIT because it's changed, it's bad, or you didn't find it. It's not in the hash table. Okay, fall through. At this point, well, if you didn't find it in the hash table, or you found it and it was bad and it's been deleted, if the JIT control is run or smaller, well, you can't change the hash table. So we're done. Go away. No value. We finished. The DL function and pointer is null, and we abort the JIT. We're not going to use the JIT. Okay. Now we go into the next phase is, well, maybe it's been compiled before. Let me try to load it. To load it, I first have to construct the file name. And that's what this switch case does, depending on the family of are you assign, apply, MXM, and so forth. And I have to, this is now the slow path. So far, everything has to be extremely fast to this point. Like right here, this is the typical greased lightning path right here. I look it up, I find it, and I go with it, and that's it. 99.99% of the time, that's what you'll do. And in a tight loop, you'll finish with this. Okay, now we say, well, I got to talk to the file system. I got to either compile it or load it. If it's not loadable, I'll compile it and so forth. So I got to build a file name. I macrofy the name. So I have the name of the kernel like MXM. The prefix is JBJIT. So it's looking for JBJIT MXM, and then it's got the kernel name, which is like .3 or something, or Saxby. It's going to be, whoops, say it's GBJIT MXM something. Let's see, whoops. JIT, let's see. Oh. Oh, there's 2 underscores, right? Oh, it's not MXM. They'll have, say, specific kernels. We're below the level of MXM. We might be the .3. So this kernel name might be AXB.3 or reduce. If we're looking at the reduce case, it's JIT reduce. So here's all the JIT reduces. That's the reduce is this name of the kernel. Or no, I'm sorry, that's the total name. This output, I'm sorry, this output is, say, this entire name. This is reduce. JBJIT reduce. It needs, how many digits is this? 1, 2, 3, 4, 5, 6, 7, 8 digits for reduce. And that would, if you go up here, you'll see the reduce family, or is that 7? Sorry, that's 7. I need 7 digits. So it's going to be 7 digits name, and it's going to be this encoding. This is the O3F1, and the suffix will be myCX plus. So I have to build this file name. Okay. And I'm loading it, or it might not actually be there, so I may have to compile it. So I lock it first. And this is to protect different different GraphBLAS processes from just happening to compile the same kernel at the same time. Like if 2 processes want to come in here and they have the same case, it's a reduction using myCX plus, which is a complex plus reduction. And it's the O3F1 instance, whatever the heck that is. I have no idea. Okay, it's this case. It's A is sparse. It's of type MyCX. It's a user-defined type. There's no zombies. You know, everything has been encoded, and then the strings are in addition to that. It's a reduction of for this case with this user-defined type. The suffix here, by the way, does not include the name of any data types. The suffixes are only needed for user-defined operators. And user-defined operators, if they do use user-defined types, which they don't have to, they can use built-in types. If they do use any user-defined types, well, there's no typecasting. So by giving the name of the operator, it defines the names of the types. That's the type. You can't cast automatically. So I don't have to put the op type name into the string, just the operator. That's all I need. And if it's a semiring, I have to put the monoid and the multiplicative operator both. But here it's just say an operator which is the operator of the monoid is called MyCX plus. Okay. So I lock it. I have a separate file, a lock file, that's going to have the same name. So in fact, it's going to be in this lock folder. It's going to be in lock. There's going to be a file here. Oh, it's not there. That's curious. Oh, yeah, that's the name of it's only with the hash code. So it's sorry, it doesn't have the full name. So I lock the thing. It's just named with the hash code. It's one of these. I'd have to look at which one it is. So I lock a file. If it fails, of course, well, you can't lock the file system. You can't lock a file with the file system. So having trouble. And whenever I have trouble in the JIT, I turn the JIT off. Because I don't have to use the JIT. And this is proven to be a little bit of awkward user interface issue where CDMXM uses a semmering and whoops, the file system is full, you know, file permission for that file system, or you've got a semmering who's, you know, maybe the type is not defined, or you try to compile it, something break, like you get compiler error, you compile it and compiler error fails. Well, I turn off the JIT. So it doesn't happen in a tight loop because I could call a generic kernel and get it to work. So I punt to generic. And to avoid repeated error, like, you know, you want to be, if you do MXM in a kernel in a loop 1,000 times, and I'm going to try to compile 1,000 times. Let's not do that. Let's only fail compiled once and then punt to generic. So I'll turn off the JIT for everybody to say, whoa, something happened here. There probably needs to be another mechanism here to say, well, if something failed in the JIT, please treat that as a fatal error, because I don't want to. I want the grease lightning. I don't want you to punt to generic. Just give me a hard failure. I should have a way to control that. I don't. What error do you wish to get if the JIT fails? Like compiler error.
Is there some burble that in the event that
The
someone can look at the
burble will
log?
tell you. The burble
Yeah.
will tell you. Yes. The burble will tell you, and I have cases like that. I mean, examples of that. Okay. Now I have another worker. This is layers of workers, I guess. This is a load worker, load two worker. Now I've decided to, I have to load the kernel, compile it if needed. So that's the load worker's job. I just broke the function up into different. I guess that, I wouldn't have to. It's just called once. It's just kind of big. Otherwise, it starts to get big. So I just broke it up. This is 184 lines of code. It could have been stuck right there, but I didn't do it that way. So compile it, load it, and then unlock it. So this is paired. This lock here is paired with this unlock. So it's kind of acting. That's why I put this as a separate function. It's kind of acting like open close bracket. It's like open the critical section, close the critical section. So here's the rest of the work. Now I've decided already in a critical section, I've decided I need to either load it, and if that fails, I need to compile it. So let's try loading it. So I build the name of the .so file, and I try to do DL open, which is not a call to DL open unless you're POSIX. This is calling to the gbfile.c. It's got a gbfile DL open, which is DL open if you're POSIX, and it's, I forget, something else on Windows. Okay. And the lib suffix, this is a compile time constant. It's .so if you're compiled on Linux. It's .dylib if you're on the Mac, and it's .dll, I guess, on Windows, I think. Okay. So I try to DL open it. If I DL opened it, I've loaded it into memory. But this is the first time I've seen this kernel this run. So now I'm gonna say, okay, library I just loaded, give me a function to your query. Give me a pointer to your query function. And then if I find it and call it and compare it and it matches, we're good to go. If I can't find the query function, that would be weird. Or if the strings don't match, then we're not okay. I close it and I remove the file. I remove the compiled library I just loaded. It's deleted. This is the compiled library. It may not be there. So none of this happens. If I find it and it's bad, I delete it. And I set the DL handles to null. So now I said, I pretend I didn't have it now. Now I'm going to compile it. So, well, but sorry, you don't have the compiler the JIT turned on. So to get to if you've gotten to this part and you return before getting to this part, say the JIT is set to load. Okay, I could load the compiled kernel, but if the JIT control is set to load and you loaded it, you're good. If you set to load and I didn't find it to load, well then I have to compile it, I stop. I say, no, I'm not going to compile it. I can only load previously compiled kernels. So now I've got to write this file. Whoops. Now I got to write this file. Write the file and compile it. So this is where you're going to see a lot of the macrofies. All this stuff, all this outputs of strings come from the macrofy process. You've seen the encodify and the enumify. This is now the macrofy. You've seen macrofy up above when I had to macrofy the name. Macrofy means build me the string or the file of the thing I want, of the code, of the whatever. That's what I mean by macro. I macrofy a name. I could have called it something else, but it's building the string from its component parts. I've already done that. I have the file name. So now I have to create the source code. The file type here, well, I have two backends. This is one of the few places where I have to specialize. I'll specialize also later. The name of the file. Is it a .c file or .cu file for CUDA? And that's just a simple check. So create the file, try to open it. If we let's see. if I fail to open it, like you don't have file permission, these compilations are going to fail. And at the very end, if you can't even write the file, you won't be able to load it. So this will return null. So I don't have to have an else case for this. So this is every CUDA kernel, every OpenMP kernel. Source code is built right here, one place. All of them, both CUDA and OpenMP, one place. And to do that, I have to call the Macrofy suite of functions. This is the entry into these suite of functions. So let me maybe start this in another window. And so what do those look like? These are all so the main entry point to the Macrofy is both the preface and the family. The preface simply, let me pull this up again. There we go. The preface is just producing these. And it's different for CUDA because it adds a pound define, hey, it's a CUDA kernel flag. Otherwise, that's it. So I put in, some comments to you notice what you're looking at, and the header, and I also have a preface because you can put in extra pound includes here if you want from the user level. You can say, Tim, every time you compile a JIT kernel, add pound include my wonky math.h. Okay, I'll do that. Because maybe you need that to compile your kernel. Your user-defined operator may need that. So that's the preface, and then I go into Macrofy family. Macrofy family is the master macrofier. It's going to macrofy everybody. Here we go. It's well, what family are you? It's just a single switch case. That's going to say, we're in the reduce family. So I'm going to macrofy reduce. So let's go to GB macrofy reduce. And you notice there's only 1, 2, 3, 4, 5, 6, 7, 8, 9 different kinds of families. Reduce is, here's the family. It's got the code. It only needs now this macrofy. In some cases, like the MXM family needs a bunch of things. Everybody needs the code. Well, I guess these don't need the code. And the MXM family needs the summaring, and it needs 3 different types. The reduce family just needs a monoid and a type. And that comes from, there's the monoid and the type, and but I don't actually need the rest of, I don't need it to summaring, so I don't use it. But I pass in all these things, and then I take out the macrofy reduce. So let's go to GB macrofy reduce. The job of this function is to now produce, whoops, what is happening? Wait. There. I don't know why my terminal is acting in weird ways. I'm not sure. My terminal app on my laptop here. This is strange. Oh, now this is not moving. What?
Weird.
That's weird. I've never seen this before. Oh, now it's moving. Okay. I don't know what's going on. Okay. It might be the Zoom share. I don't know. The goal of this macrofy reduce now is to produce this whole file. Except I don't think it's going to produce the query. I think that's a separate phase at the end, if I remember. Yes, it is. See, macrofy query is down here. So I'm going to produce, actually, it's this printf is separate. So it produces all the way down to here. So this piece right here is produces this. So Macrofy family, then the job is to produce this. I have to produce lots of things. So here's the reduce. I first have to get the code to know what is I'm doing. I've encoded this already. Which reduction operator, which ID as in bits. I'm unpacking the bits that I packed for the code. This is that O3F1 thing for this instance. This code right here. I'm unpacking those bits. Okay. And then I go through and I first have to macrofy all the type defs. So, okay. So it has one, whoops. It has one type def. There could be more. This has one. There could be two. There's a type of the A matrix and a type of the monoid Z type, the type that the monoid uses, and they can be different because you can typecast between the two. Not for user defined, but you can typecast it otherwise. There are up to 6 types. This one's only using 4 of them. And I have to be careful because those 2 types could be repeated. In fact, for this one, they would be. So I check them. Whoops, I already typed that. I'll skip it. So macrofy the type defs. I macrofy the monoid. To macrofy the monoid, I first make sure the type has been macrofied. Oh, but it already is. It's up here. This is, let's see, what have I done? Oh, no, this is not a type def. This is giving this defined. So I'm basically building up all these pieces. So here I macrofy a monoid. Now the monoid then comes all the way down, I don't know, probably all the way to here. So there's everything I need to know about the monoid. I need to know the actual function, the static inline function. This is a macro because I want to be able to, this is either static inline or it's underscore underscore device underscore underscore static inline for CUDA. Because this could be a CUDA static function, device function. And I repeat the string so I can query it later on. And then I have all the macros that define everything about this monoid I need to know. Now this monoid, this macrofy monoid, you'll find other places like the semmering. I'll call the same function. I'll call macrofy monoid because the monoid, you know, I have to macrofy monoid, stick it in the MXM kernel. So that happens here, and I could dive into this and maybe be useful to do that. Why don't I just dive in? This macrofy type is super simple. That's just producing 1 pound define. You see, I don't. I mean, this is like a C template, right? What's a C template? Pound define a type, pound include the source.
Right.
So I could have done this as a type def GBZ type as my CX. I didn't. I just made a pound define instead.
Well, and it's so heavily used. I mean, it's a fine pattern. Yeah.
Yeah. It's very simple that way.
Just to interrupt a quick time check. I know you said you had a 4 o'clock. You got about 30
Oh,
minutes.
yeah.
We could split this session into 2 as well.
Yeah, we'll need to do that. Let me dive deep and I'll stop. I'll dive deep into macrofy monoid and I'll stop here. How about that?
Okay.
Because I'm almost because it's kind of an interesting deep dive here. So let's look at GB macrofy monoid. How do I macrofy a monoid? Okay, to macrofy a monoid, I first macrofy the binary operator, and then I macrofy the identity value and the here's the identity value. There's special cases for complex for doing assignments. Let's see, to get the monoid value, identity value, and the terminal value. If a monoid is terminal, it has a short circuit like stop here at this value and it'll never change any further. That's what I call the terminal value. I macrify that as well. And then let's see, what do I do? I have special cases that I tell the kernels that I'm doing these special cases. And then I create macros for atomic operations, and I create macros for CUDA as well later on. And this I put in everybody. Even this C code gets these CUDA atomic types because I'm not going to use them. So who cares? So I call this for everybody, even the CPU kernels. It's just simpler that way to have the same almost the same code. But one big thing here, though, as I dive into, is I macrify the binary operator. So I've already encodified it. Now I'm doing the opposite. I'm converting the code into a string. So how do I do that? Well, if it's an ISO valued output matrix, there is no operator, does nothing. If it's user defined, I have to emit the call to the, and where do I have it here? Then this is user defined. I have to put this in, a call to the function. But if it's built in, then this macro, like for plus real, becomes this. And the update becomes z plus equals y. So the u string is the op equal thing. And some of them don't have it, so I don't use it. And so this one doesn't have that, so it just has a call to the function, the static inline function. But I have every built-in operator defined as a string. It's like I'm writing my own compiler here. The bits operations and the I mean there's a lot of them. So the macrofy monoid has to first macrofy the binary operator, and then it goes in and macrofies, say, for example, the identity value. Let me just look at this really quick, and then we'll stop. I think at this point, we're getting to the point where we finished so macrofy an ID value there, that's it. Okay. This is going to produce the string for some identity value or terminal value. Like, is it 0, 1, true, false, int32 max, infinity, minus infinity? These are all the scalar values for every built-in monoid, their identity value and or their terminal value. I've encoded them all. And by default, I don't produce them at all. Now, if it's user defined, it's a little bit different. If the thing is user defined, I have to let's see. What do I do here? Yes. If for user defined monoids, I don't do that. I have to actually produce a bunch of bytes. And that's what you see here. Because all I have is 16 bytes of, in this case, zeros. I detected that when you defined the monoid, you gave me an identity value of all the 16 0 bytes. So I can use memset to set them all to 0. I can't just use a simple assignment of 0. I guess I could, but I mean, it's a struct. 16 bytes of 0 for a struct. So just memset thing. That's how I declare an identity value. For the built-in types, I can use an equal sign to get the identity value. And same thing with the terminal value. So that's a monoid. That's how I macrofy a monoid. And it all peels down into these different layers. Macrofy, reduce, unpacks the code, macrofies, creates the strings for the type test, creates the strings for the monoid, and then keeps going. It creates the strings for the input matrix, the A matrix. And then this is doing some algorithmic stuff. It's going to look to see which algorithm to use because it's setting the panel size for the reduction to reduce in chunks. And then finally, there's the definitions, and then there's the kernel, and that's it. So that's reduce. That's the whole thing, basically. You haven't seen how I compile this thing, but this is how I generate the file. And there's lots of families. I haven't looked at every family, but they're all kind of in the same vein. I have to macrify all these different things like casting and casting inputs and outputs, casting monoids, casting how many values do you have in your matrix? I mean, casting string, making the strings for them to write to the file. And all of these typically will just simply, they just write to the file directly. They create a string, write to this output file. And the only one that doesn't is the macrify name function does not. And maybe I should call it something else. This just does a sprintf. I mean, you should call it stringify instead of macrify. So that's the whole kernel, except the query. I could save that for later. I could stop right here. So,
Cool. It's
and then
crazy seeing it at this level.
yeah,
It's just so much.
there's so much. It really was.
Yeah.
It took me
It's like I
months to get
created
this to work.
a meta compiler.
Yeah, yeah. And then once I create the file, I got to compile it. How do I compile it? Well, that's open into like, are you CUDA? Are you OpenMP? Do you want to use CMake? Do you use shell out to the compiler directly? That's done here. So if
Oh
I
yeah,
have different backends, I'll have to break off to different compilers.
sure.
But I could do that right here. Like I do this. Um,
Okay. Well, I think we can pick up at session 7 if you think this is a good stopping point.
I think this is a good stopping point. This
Yeah.
is an interesting little thing. If you look at the Jitifier to see where does it talk, what does it do with CUDA? That's it. That's
Yeah.
every word that mentions the word CUDA in the JIT. I mean, it's so very terse.
All right. Well, I'll stop
And
here.
so, yeah, let's stop here.
Do you want to stop? Yeah.